the topic for the day is types of queues in data structures. So these are basically the various types of queues that we encounter in data structures: the simple queue, the circular queue, priority queue, and the double-ended queue, right? So the simple queue, or the linear queue as it is also known as, follows the first in first out principle, and elements are inserted from the rear and removed from the front. As far as applications are concerned, simple queues are used in task scheduling, resource sharing in operating system and order processing systems, besides other applications. Limitations include wastage of memory, as the space is left by dequeued elements, which is not reused, as would be seeing in the coming slides. So here you can see diagrammatically a queue in which the enqueue operation is shown to take place from the rear, while as the dequeue operation, or the elements are removed from this end, which is known as the front end, right? So we have another queue which is known as a circular queue. It is a linear queue where the last position connects to the first position, forming a kind of a circle, right? This helps in reuse empty spaces. Applications include memory management, traffic light systems, and buffer management in computer networks. Advantages include efficient memory utilization compared to a simple queue, right? So let us take an example to understand the things we have just discussed. So here I have taken a queue, a linear queue, which is named as a QUE, right? Max represents the total number of elements that can be inserted into this queue. Say in this example, I have taken an array or a queue with a capacity of 6 elements, out of which 2 have been removed supposedly, and the rest of the 4 elements you can see here. So front is pointing to this element which is at index 2, while as the rear is pointing to the index 5, at which currently 30 is stored, right? Do you think there we can insert some more elements in this queue? It should be the case, but let us check the code that we generally write for a linear queue. So here is that enqueue function. So if an element, say n, is coming, the element is to be inserted into this queue. So what is to be checked before inserting that element into the queue is that rear should be less than max minus 1. Then only insertion would take place. So let us say here max is 6. So 6 minus 1 is 5. R is also 5, as you can see in the diagram. So for R is not less than max minus 1, or 5 is not less than 5, right? So the control would go to else, and print and a statement of overflow would be printed, right? Mentioning that no more insertions can take place in this queue, because we have already R reaching the point beyond which no elements can be inserted, right? Even though there are spaces or vacant spaces that elements can be inserted into, right? So this problem is overcome by the usage of circular queue. Let us see from this example. So for the same set of values where f is equal to 2 and r is equal to 5, and for same set of values, let us see what our enqueue function looks like in case of a circular queue. So here, as you can see, you are checking the overflow condition in a different way. So f is equal to r plus 1 mod max, right? If this is true, then an overflow condition would be printed, else the element would be inserted, right? So let us check this. So f here is 2. 2 is 2 equal to r plus 1. What is r? R is 5. What is 5 plus 1? 6. 6 mod 6. 6 mod 6 is 0. Remember that your mod returns the remainder out of the division operation. So here 6 divided by 6 would be what? A remainder of 0 would be returned. So I am saying if f, which is 2 in this example, if 2 is equal to 0, which is not true, right? So control would go to else part, and it should insert the value of n into this queue, right? At what position? At now, if you look here, that R is incremented in a different way as compared to the ordinary or the linear queue. In case of linear queue, you simply pre or post increment the R like this, R pointer, the rear pointer, and then you insert the element. Whereas in case of this circular queue, you increment the R in this way, R is equal to R plus 1 mod X. So R would now be 0, and at 0th position 11 would be inserted. I am assuming here that n is equal to 11, or the element to be inserted is 11, right? So what changes would occur to this diagram? Yes, R would now be 0, because that was the latest element which has been inserted, 11, which was inserted at the index of 0. That would be the value of R. So F would be 2 and R would be now 0. Say we are trying to insert another element. So let us see if F is equal to, what is R? R is 0. 0 plus 1 divided by max, right? So what would be the answer? Answer would be 1, because this time remainder out of this would be 1. So R would be F. F is 2. 2 is not equal to what? 1. So no overflow condition would be displayed. Instead, the control would go to the else part, and the next element which we are trying to insert would be inserted at the index of 1, right? So if you again try out this code, this time it would show the overflow condition, or the message queue is full. But at least we were able to retrieve the values or the vacant spaces which otherwise in case of linear queue would have been wasted, right? So that is basically the advantage of circular queue over the linear queue. So the next queue that would be discussing is the priority queue. A priority queue is an abstract data type that has all the features of a regular queue, with the exception that each member in the queue has a unique priority associated with each element, right? The elements that are retrieved first are those that have a greater priority, right? So over to the types of the priority queue, we can have an ascending priority queue where elements with a lower priority value is given the higher priority in the priority list, right? Similarly, we can have a descending priority queue, in which case the elements with a higher priority value is given a higher priority in the priority list. So we would be doing things this way. That means we would be implementing the descending priority queue for our example. So let us go to the characteristics first, and then we would move to the implementation. Characteristics of a priority queue: each item in the queue is homogeneous, that means of the same type, and has specific priority associated with it, that would be discussing shortly. The element with the higher priority is dequeued before the one with the lower priority. Elements with the same priority, because there can be elements with the same priority, are served according to the first come first serve principle, right? Let us go to the implementation now, right? So I have assigned VAL to the value of the queue elements and PRI as priority, as their priority. So 5 to here means that 5 is the value and 2 is its priority, right? And we are trying to insert it into this queue, right? So 5 would be inserted. For the sake of simplicity, I am only inserting the values and not showing up the priority for each elements, which may be shown later on, right? The next element in the queue or to be inserted in the queue is the 4 with the priority of 3, right? So 4 would be inserted here, but as you guessed it right, we should have this 4 before 5 because 4 has got the higher priority. So that would need some kind of rearranging like this. So would be doing this. So 5 has come here and 4 has come down to this place, right? Because 4 has the higher priority, right? What about this 6? Now this 6 has even higher priority than those two elements. This should again trigger a rearrangement of elements. First 5 would come here and 6 would come here, and then 6 would go to this place and 4 would take its place. Next 3 would be inserted as it is because the priority is less than all the elements that are currently in the queue, right? So no change of order of elements would take place in case of 3, but here a massive change is expected because the element 2 has the highest priority among the elements which are currently in the queue. So what should happen? 2 which has just come in would take place of 3 first, and then it would take place of 5, and then it would go down to this place replacing 4, and lastly it would replace 6 also to take the frontmost position. So remember here that while dequeuing, we do the dequeue operation or remove elements from the front end. 2 would be the first one to be removed, right? Now for the sake of clarity, I have added the priority. So 2 has the highest priority, followed by 6, 4, 5 and 3, right? What about the code? Let us concentrate on that. So I have, instead of a simple queue item, I have here used composite data type because I need to store value as well as its priority. Since I have to store 2 entities or 2 values for each element, so that made it necessary to use a composite data type like a structure which has been named as PQ in this case. So struct PQ type Q. So Q's type is struct PQ, right? And max is the max number of elements, of course 100 here, but you can have a different value. And F, that means rear and front pointers have been initialized to -1, as is generally the case with queues, right? It basically says that there are currently no items in the queue. T, let us see later on what it is used for. It is a temporary. This is the enqueue function with respect to the priority queue, right? So I have taken a snapshot out of the discussion of the previous slide, wherein we tried to, or we saw how the elements get inserted or rearranged in case of a priority queue. So here I am assuming that 5 and 4 with the priorities of 3 and 2 have been already inserted into this queue. So the next item that is to be inserted in the queue is 6 with the priority of 4. Let us try to insert this value into this queue while doing a hand simulation of this code, right? So first of all, we'll be doing if we are within limits, and if it is the first element, which is possible only if we have started with an indices of -1 for both F and R. That means front is -1 and R also is -1. In that case, we increment front, as you might have seen in case of the queue implementation in general, right? Other than that, we generally increment the rear pointer, right? So with reference to this diagram, you can see that F is pointing to 0 and R is pointing to 1 because we have only these two elements. So let us try to insert the value of 6 with a priority of 4 now. Let us see how it works. So T, the temporary variable, has been assigned the value of R, which is rear. So rear is 1, so T would be 1. So what I am saying is that while T is greater than equal to F, which is true in this case. Why? Because t is 1, 1 is greater than equal to f. Now remember why we are giving reference of f here. You can do the insertion or the comparison processes up to what? Up to 0, beyond which there would be negative indices which are invalid in case of arrays, as discussed time and again. Right? So array index starts from 0. So 0 would be the value index and the values higher than 0, that is 1, 2, 3, 4 and so on. So that is what I am trying to say here, that you should remain within the limits, and the other condition for the rearrangement of elements would be as long as the qt dot priority, qt means q1th, q1 is this element, and its priority is less than the priority of n. N is the element which is to be inserted, which in the current example is this element. That means n dot val should be 4 and n dot pri or priority should be 4. So this rearrangement, that means if we want to insert 6 here, it should be inserted at this place, or we will have to move 5 to that place and insert 6 here, and the same process would be repeated for the 6 and 4. That means 4 should come here and 6 should go up to this position or the 0th position. So for this priority, n dot priority is 4 and qt or q1 dot priority is 2, right? Because priority of 5, which is currently the rearmost element, its priority is 2. So 2 is less than 4. So what should happen? qt plus 1. So q1 1 plus 1 rather, q2 dot value should be equal to q1 dot val, and q2 dot priority would be equal to q1 dot pri, or the priority. In other words, or in simpler terms, this 5 would be moved to this place along with its priority. As I told you earlier also, I am, for the sake of simplicity, I am only showing you the values or not the priorities, right? So 5 should move to this place, right? So 5 has moved to this place, but this 5 is still there, as things would get clear in the coming moments, right? So the current state of this queue would be 5 and 5 and 4, right? So the control would go back to this while, but not before doing a t minus minus. So control would go to here. What is q? Now what is t rather? T is now 0 because t was 1, or it was initialized with 1. Now it should go to 0 by virtue of this decrement. So is t 0 greater than or equal to 0? It is not greater, but it is equal. So this is true, this part done. And now at the same time we have to check whether qt, what is qt? q0 dot priority, what is at 0th position of q4? What is 4 priority of 4? It is 3. So this part is 3. What is n dot priority? N means the element that is coming, that is to be inserted. That means this. What is its priority? Its priority is 4. So 3 is less than 4? Yes, of course. So now the element which is at qt, that means 4, should go to qt plus 1. So it would come here, right? That is why I was saying that if 5 has come to this place, so 5 is already there, so 4 should now go to this place, right? So qt plus 1, that means q1 dot value should be equal to what? qt dot value. That means this 4 should go to this place, right? So 5, assume here 5 is here and 4 has come here. Now t minus minus would make t equal to what? Minus 1. So this condition would now be false because t is already what? T is minus 1. It is not greater or equal to f. So control would come out of this while loop, and q t plus 1. What is t? T was minus 1. Minus 1 plus 1 means 0. So q0 would be equal to, or the value of it would be equal to n dot value, which is 6. And priority also would be stored in q t plus 1's priority part, right? So 6 would go to this place, right? So 5 has moved to this place, 4 has moved to this place, and 6 has moved to this place because of the higher priority. Now you can hand simulate the code for other values as we have already seen in the previous slide, so that the things get clear. So lastly, what I have done is that I have done a plus plus to all, because one more element has been inserted in the queue. So rear should now be pointing to 2, because the latest element would be here, or the number of elements have been incremented by 1, right? So this else part is of this if, depicting overflow if this was the condition. That means if f is less than max minus 1, this should happen, else it should say a condition of overflow has occurred. So lastly, we would be taking up the double-ended queue, which is a type of queue that allows insertion and deletion of elements from both ends. Its operations are not restricted to one end, like in case of a linear queue. So as you can see in the diagram, from the front end you can do the insertion as well as the deletion operations. Same for rear end, from which you can do the insert as well as delete, right? This is against the concept of a linear queue, wherein from front only deletion takes place, while as from the rear insertion takes place. So the difference basically is that you can do both the operations from both the ends. That is why it is called a double-ended queue, right? So if we can see certain features, so bidirectional operation means insertion and deletion can occur at both the front and rear ends. This flexibility makes it suitable for applications like undo operations, etc., right? So as far as the types are concerned, we have the input restricted queue, where insertions are allowed at only one end, while deletion can occur at both ends. Clearly concentrate on this point, that only insertions are allowed at one end, but deletion can occur at both ends. Now output restricted, as you guessed it right, deletions are allowed at only one end, while the insertions can occur at both ends, right? So applications, task scheduling and palindrome checking. And obviously there would be some more applications. Advantages include it provides high flexibility and efficiency for managing data where access to both ends is necessary, right? So widely used in algorithmic challenges due to its dynamic nature. So if we can just have a snippet of code to clarify things, here I am saying dequeue.add first. It means it would be adding from front. Similarly, if I say dequeue.add last, it means I am doing the insertion part, the enqueue part from the rear. Same for accessing elements. If I am saying dequeue.peek first, it means I am displaying the element from the front-most element. Similarly, I can do the same from the rear end. Similarly, for the remove first and remove last, this removes the element from the front and this removes from the last, right?